So far, we've talked about the valence bond theory or hybridization theory for describing why molecules become in tetrahedral, trigonal planar, stuff like that. But we haven't talked about the other one. And the other model is called molecular orbital theory, or MO theory. Now, MO theory is a much more comprehensive theory. It's really, really powerful. It accounts for a lot of things that valence bond theory does not. So, for example, a molecular orbital theory, and by the way, on the right is an example of a molecular orbital theory. Molecular orbital theory will account for things like paramagnetism, which is if there's unpaired electrons in the molecule or not. It will account for things like color. It does a great job talking about bonding. Lots of interesting things. In MO theory, the atomic orbitals, the 1s2, 2s2, etc., they are delocalized into molecular orbitals. So what that means is the atomic orbitals are essentially mixed together and molecular orbitals pop out. In the diagram on the left, the far left, the orange orbitals, that's a 1s2, 2s1 atomic electron configuration for lithium. So the left-hand two orbitals are just a lithium atom. And on the far right, you have another set of lithium atomic orbitals, another 1s2, 2s1. And it's in the middle part here that you make the MO diagram, the molecular orbital diagram. So notice here how in this molecular orbital diagram, the left and the right showed the individual atoms. And then the middle part where this delocalization, the mixing is happening, that's where you make the molecular orbitals. This is going to be the way to interpret these MO diagrams. In a molecular orbital diagram, you can have bonding orbitals, antibonding orbitals, and non-bonding orbitals. In this class, we're going to talk mostly about bonding and antibonding molecular orbitals, but non-bonding orbitals are possible too, but we won't see a lot of them in this class. MO theory is the bomb. It is so cool, and when it works so well. However, the problem with molecular orbital theory is that it's really, really complicated. Even with today's supercomputers, some of these calculations take incredible amounts of time to have happen. Now, one day in the future, I hope you all will have the TI 2000 calculator or something equivalent to it, where you can just boop, 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 enter in some information, and pop out will come out the molecular orbital diagram for some of these molecules. However, we are not there yet. Even iPhones and stuff and Super Samsungs aren't going to make this happen quite yet. Unfortunately, darn it. So anyway, in the meantime, we can still talk about MO. What we're going to do is we're going to look at very simple examples to figure out how this works. So we're only going to look at diatomics, which means two atom systems. So we'll look at things like H2 and F2, stuff like that, but we won't look at CH4 because that has 5 atoms. We're only going to look at two atom system. And also, we're only going to look at diatomics from the first and second periods only. So we're only going to use atoms up to neon. We will not be looking at, say, chlorine, Cl2, or, bromine, Br2. Those are beyond the first and second periods. So we're only looking at diatomics up to dineon. It does seem kind of limited, but it will give us an idea what's going on. And then in future courses, when you do have the TI 2000 or a powerful computer, you can do more with it and you'll make sense of what you're seeing.
Nitrogen is not magnetic. It is diamagnetic. All the electrons in the molecule are paired. Oxygen, however, interacts with a magnetic field because it is paramagnetic. This physical property indicates that molecular oxygen has unpaired electrons. Molecular orbital theory accounts for this fact, but valence bond theory does not.
So this is kind of a cool little video that shows the utility of MO theory. So first of all, that thing they were pouring the liquids through, that's a magnet, all right? And the magnet is pretty strong, needless to say. But anyway, they put dinitrogen through and no problem, N2. N2 just goes on 2. But oxygen, O2, in a liquid form, which by the way is really unstable. You got to be super careful, keep it super cold. But anyway, they put dioxygen through and you can see it kind of like sticks there between the two magnet heads. And that shows that dioxygen, O2, is paramagnetic. Diamagnetic things just go right on through. They don't care about magnetic fields, but paramagnetic things will stick. And why that's so weird is that if we drew a Lewis structure for O2, and I encourage you to do this, all right? Well, oxygen has 6 valence electrons. There's 2 of them, so that's 12 valence electrons. Divide by 2, 6 pairs. And when you draw this out, O2, draw a bonding pair between the 2 oxygen atoms. You've got 5 more pairs. Outer atoms first, and there's really not an inner atom, so we'll just do that. But you can see that the left oxygen only has 1, 2, 3 pairs. You have to have 4, unless it's boron, beryllium, and gallium, those kind of things, and this is certainly not. So what you do is you take away that lone pair, and you put a bond in right there. So oxygen, diatomic oxygen's Lewis structure looks like this. Each oxygen has 2 lone pairs. There's a sigma and a pi bond for a double bond in the middle. That's fun, but there's no odd electrons. We saw an example in the last chapter of NO2, and it did show literally the odd electron by itself. Oxygen's Lewis structure does not indicate that it's paramagnetic, but molecular orbital, we're going to see, does show correctly that oxygen is paramagnetic. It should stick to the magnet. So if you were just looking at the Lewis structure wouldn't help you here to determine the magnetism. It would give you an incorrect answer. But molecular orbital theory will. And again, MO theory, super cool, very, very complicated sometimes to analyze, but this is going to be one place where we can, even we in our class can see how, woohoo, MO is really cool. It's the wave of the future. And if you see an ad for the TI 2000 that does MO calculations, please email me right away. I would give you extra credit. Anyway. In molecular orbital theory, there are 4 principles that have to be followed, and we'll go through the principles to kind of lay the groundwork here for what's going on. Principle number 1 is that the number of molecular orbitals must equal the number of atomic orbitals, and there's lots of reasons why, but essentially the number of atomic orbitals you put in equal the number of molecular orbitals you get out. So if you put in 2 1s orbitals from 2 hydrogen atoms, you're going to end up with 2 molecular orbitals in the H2 molecule. If you put 2 1s orbitals and 2 2s orbitals from 2 lithium atoms, then you're going to end up with 4 molecular orbitals in Li2. So remember, like lithium is 1s2 2s1. There's a 1s and a 2s orbital per lithium. So 2 atomic orbitals plus another 2 atomic orbitals from the other lithium makes 4 molecular orbitals at the end. No problem. So let's say that you combine 2 oxygen atoms together. How many total molecular orbitals would you expect? This is the kind of thing you can think about. So oxygen is 1s2, 2s2, 2p4. So each oxygen has 1 1s. It has 1 2s. But if you remember the 2 p's, there's actually 3 of them. You can hold 6 electrons, 2 electrons per orbital, all right? So there's 3 2p orbitals per oxygen. So that means that each oxygen has 1 plus 1 plus 3, or 5 atomic orbitals. So since there are 2 oxygen atoms, that means there's going to be a total of 10 atomic orbitals. Atomic orbitals equals molecular orbitals, should be 10 molecular orbitals. All right. So oxygen has a 1s, a 2s, a 2px, a 2py, and a 2pz. So 5 orbitals total times 2, 10 molecular orbitals in O2.
The bonding molecular orbital has greater electron density in the bond region. The antibonding molecular orbital has reduced electron density in the internuclear region.
When two atomic orbitals make two molecular orbitals, you must always think about, as a scientist, not creating or destroying any energy. First law of thermodynamics still in full force here. So what happens when 1s orbitals come together is one of the new molecular orbitals, there's a lot of electron density between the two atoms. And the lower picture right here, this part I'm highlighting, this is the orbital overlap. You're actually making a bond between the two atomic orbitals. And because the two atomic orbitals are smashing into each other, this is a sigma bond, all right? And in molecular orbital theory, we call this a bonding molecular orbital. So a bonding molecular orbital is just something that makes the molecule more stable. You're saving energy. But if this one is saving energy, you must have something that's using up energy. It's the opposite process, because remember, you can't have any energy created or destroyed. So the two 1s orbitals will also interact in a way to create an actual node between the orbitals. Now, if you have a node, that's no glue holding the two atoms together. That's going to destabilize the molecule. And we call these kind of molecular orbitals anti-bonding orbitals. Notice the symbolism here. Bonding sigma means that, yeah, you're going to save energy. That's a good kind of orbital, makes the molecule stronger. But there's also anti-bonding sigma star. That little star right there means that it's anti-bonding and it doesn't stabilize. So if you want a molecule to form, you're going to have more bonding molecular orbital electrons than you're going to have anti-bonding molecular orbitals. Bonding makes the molecule stronger, anti-bonding makes the molecule weaker. Principle number 2, the bonding molecular orbital will be lower in energy than the parent orbital, the parent atomic orbital it came from, and the anti-bonding molecular orbital, the one with this little star by it, that's going to be higher in energy than the parent atomic orbital. Once you know what the bonding and anti-bonding orbitals are, you'll start putting electrons in to see what's happening. And you always put electrons to molecular orbitals in the successively higher molecular orbitals. And what this is this is just like we did in atomic orbitals. We always filled in 1s first, and then 2s, and then 2p. Well, in molecular orbitals, we're going to do the lowest molecular orbitals first, followed by the next highest ones and the next highest ones and stuff like that. Now, Pauli exclusion principle and Hund's rule are still going to apply. Electrons in each orbital and stuff, each electron is going to have its own thing. You're not going to have any repeats. All these kind of rules will still apply for molecular orbitals.
In contrast to valence bond theory, which assigns bonding orbitals to individual atoms, molecular orbital theory assigns the orbitals involved in bonding to the entire molecule. The simplest illustration of molecular orbital theory can be seen with the hydrogen molecule. According to molecular orbital theory, the 1s atomic orbitals of the two hydrogen atoms combine to give two molecular orbitals. Because atomic orbitals are wave functions, they can combine either constructively or destructively. Additive or constructive combination of the two atomic orbitals gives a bonding molecular orbital, while subtractive or destructive combination of the two atomic orbitals gives an anti-bonding molecular orbital. The bonding and anti-bonding molecular orbitals formed by the combination of two 1s orbitals are called sigma 1s and sigma star 1s respectively. The bonding molecular orbital, sigma 1s, is lower in energy than the original atomic orbitals. And the anti-bonding molecular orbital, sigma star 1s, is higher in energy than the original atomic orbitals. Like atomic orbitals, molecular orbitals can accommodate a maximum of 2 electrons each, with the electrons in the ground state occupying the lowest possible energy orbitals. The molecular orbitals in the hydrogen molecule can be represented with lines or boxes placed at the appropriate relative energy levels. The 2 electrons in the hydrogen molecule both occupy the bonding molecular orbital. Because most of the sigma 1s bonding molecular orbital is located between the 2 nuclei, Electrons in this orbital draw the two nuclei together by electrostatic attraction. The sigma star 1s antibonding molecular orbital consists of two lobes. The majority of the space occupied by the two lobes does not lie between the two nuclei. In this molecular orbital, the region between the two lobes is known as a node. Electrons in this orbital would actually draw the two nuclei apart by electrostatic forces. Hydrogen has no electrons in this antibonding molecular orbital.
Okay, a lot of information there, but this video is actually pretty helpful, and it's going to actually make you realize why we memorized the 7 diatomics back in Chem 221. And if you remember, it's have no fear of ice clear brew, or whatever version you want to use. Have hydrogen. Hydrogen is one of the ones that naturally exists as a diatomic, H2. And this slide is going to show you finally like what's going on. So in the video, it did a pretty good job, I think, talking about how when the 1s atomic orbitals come together, they make the lower bonding molecular orbital and they make the higher antibonding molecular orbital. And notice the descriptor, it's called it sigma 1s and sigma star 1s. So the sigma is the head-to-head overlap of the orbitals, no problem. The star means, of course, antibonding, but the 1s means that they came from 1s orbitals. And we're going to see eventually here some other orbitals that come from like 2s, so that's kind of helpful too. But anyway, when the 1s orbitals on the hydrogens come together, then they make sigma 1s and sigma star 1s orbitals. So this is the molecular orbital diagram. And initially, there was like a single electron in the left hydrogen and a single electron in the right hydrogen. Then in the molecular orbital diagrams, they both went to the lower bonding molecular orbital. Electrons always go from lowest to highest orbital. One is spin up and one is spin down, all right, to give them opposite spins. But guess what? This is actually the molecular orbital diagram now for H2. And notice how both electrons in the individuals saved energy making H2. This is why H2 is the dominant form of hydrogen. You save energy making the H2 versus the individual hydrogen atoms. And that's kind of a cool thing. So we would describe this then as two 1s electrons from two hydrogen atoms occupying the sigma 1s bonding orbital in H2. And again, the atomic orbitals are just these guys. The bonding molecular orbital is this one right here. The anti-bonding is right there. And because there's more bonding than anti-bonding, H2 is going to happen, which is pretty cool. Now, was helium one of the diatomics, i.e., will there be an He2 molecule? Let's find out.